All right, so like I said, we were going to talk about those powers on your factors. So below are the graphs of power functions. Like I said, just to remind us again that when a power is even, when we have those power functions, what happens is my graph comes down. So this is like x to the sixth, x to the fourth, x squared. Each case, what we see is we come down, we touch the x-axis, and then we turn away. So that's still an intercept we have here. That's the next intercept, even though we just touch. Here, these are all cases of when we had odd power functions, so x to the seventh, x to the fifth, x cubed. We notice that we come up and we cross at that point. So we come up to it, touch, and then cross through it. And just to put this in here, there's one more of them. That'd be x to the first power. That one's just straight. But what we notice here is that when a power is even, the graph of the function touches the x-axis and then it turns away. When the power is odd, the graph of the function crosses the x-axis. Then it's happening at the zero. So all of these have a zero at zero, and so do all of these ones as well. So when it hits at that zero, like I said, if the power was even, it touches, turns away. If it's odd, it crosses. So when we factor a polynomial, the power on the binomial factors that we have is what we call the multiplicity. In other words, it is the number of times that zero is repeated. I think it's quite the one we had before, but if I gave you x minus 3 squared, x plus 2, well, we have two zeros. We have one at x is negative 2 and one at x is positive 2. So when x is negative 2, what we see is that one came from this factor, which had a power 1, therefore the multiplicity is 1. The x equals 3 came from this factor, which had a power 2. So it's kind of like it happens twice there. So the multiplicity is 2. So it's not like you go back and you have to like pop down and hit that spot again. It's a little more involved than that, but what happens is the more multiplicities you have in a spot, the more your graph kind of flattens out there. So to the left is the graph. Let me fix that here. It cut off a little bit. Of x minus 3 squared, x plus 2. So what we see is at that 0, where we had a multiplicity of 1, I just cross through it like it's acts like a linear equation. X to the 1 crosses through. This one had a square, so this is going to act like a parabola. It comes down, touches, and it turns away. So the power on the multiplicity is going to tell you how your graph is going to behave and cross at that 0. So like I said, so when you have those odd powers, it goes right through like we'd see with all our odd power functions. When it was an even power, it comes down, touches, and turns away, like happened with all our even power functions. So like I said, those power functions were governing how things behave in the long run, but they also behave how we behave when we're crossing at zeros. So even in odd multiplicities, if x minus c to the power k, and k is going to be a positive number, that's basically what it is a factor of the polynomial function. Oh, if it's a factor of the polynomial function p of x, and then x minus c, k plus 1 is not a factor. So that's a weird way of saying basically like this is the maximum amount of multiplicity I can have on a factor. So that's really what it's telling you is like if I have x plus 3 to the power of 5, then there shouldn't be an x plus 3 to the power of 6. That's all we're saying. It's like this is the maximum power I can put on that factor. If that is so, k is odd, and then the graph crosses the x-axis at c equals 0. If k is even, the graph has tangent, which means it touches, so it comes down and touches the x-axis at c 0. Yeah, so tangent is just a Greek word to mean to just to touch. So when we say things are tangent, we mean they just touch and they turn away. At least for what we're dealing with. So we want to find the zeros and the multiplicities of the zeros and then make a rough sketch of the graph. So we have this factor here. So this one's telling me I'm going to have a 0 at 4. Because I need, like I said, if I solve this for x, I'd get 4, and its multiplicity is 3. This one right here, if I was to solve it for x plus 3 equals 0, we would find that my 0 is going to be x is equal to -3. And my multiplicity is going to be 2. So what I'm going to do is I'm just going to graph those two on here. So that is my 0 at 4, 0, and then my other one is over here at -3, 0. So first thing we're going to talk about is really what we call it's kind of give you an idea how this works is your long run behavior. So I have a power of 3 and I have a power of 2. So that means if I had a leading term, my largest power is going to be 5. So you just end up adding those powers together. If you foiled this, that's what you'd see. You'd end up with an x to the 5th at the end. So my largest power is 2. This is a positive 1. This is a positive 1. So my coefficient out front is positive. So what we're basically saying is that my leading term this is kind of avoid having to, like I said, to expand everything. Leading term is basically going to be x to the 5th because I only have powers of 1. It's only going to have power of 1, or I mean, I only have coefficients of 1. So it's going to have coefficients of 1. If I add up those powers, that's what I'm going to get. Okay. So what that tells me is that this long run behavior is going to be like this. So I know at the ends, it's doing this. So now when we talk about the multiplicities, what the multiplicities are telling me is that this one here, the first one, x equals -3 had a multiplicity of 2. So we know that we come up, we touch the graph, and then we turn away. So it's just kind of giving me a rough idea. It should be doing this. Then I still have to cross here at 4, so I have to turn around and come at it. And because the multiplicity was 3, it should be doing like that, it should be crossing. So it should be crossing more like this because it's a power of 3, so it should act a little more like a cubic shape. But that's what we mean by doing a rough sketch, is that we kind of try to figure out our leading, like I said, what my leading term would be. Okay. So this is just the actual graph, what it looks like. Like I said, we had a really rough sketch of it. Just seeing that, like I said, it comes up, bumps here, and it kind of does that like flattened out curve there, like you do with cubics, because it had that multiplicity of 3. Okay. So if you can work on 4 and 5, so 4 and 5 are just finding the zeros and the multiplicities and making a rough sketch. So I'll tell you 4 and 5. Well, 5 is a little easier to see. Your coefficient is going to be positive, so either it's going to open up like this, or trying to orient this right, or it'll be like this, so it will be the positive coefficient. And then if you can, this is just a word problem. So look at this one, use some graphing technologies to try to figure out, find these certain values that you're looking for, milligrams of, I forgot what it was, ibuprofen in the bloodstream. Okay. So we see here, we have essentially a multiplicity of 1, 1, 2, 5, 5, 6, 7, 8, 9. So we got something that's essentially like its leading term is x to the ninth. So we know it's going to have this kind of shape. Right. So if we want our zeros, we either can have x is equal to 0, x plus 1 is equal to 0, x minus 1 is equal to 0. And then we have x plus 1 is equal to 0 again. So this is what we were talking about duplicating something and wanting to get the right, we want to get the right, sorry, multiplicity on it. We need to go back and rewrite this. So this is actually x, and then we had x plus 1 to the 6th, not the 5th. So that's what that part was telling us, is that we have, like I said, x plus 1 to the 5th, but I can't go to x plus 1 to the 6th. Or if that can happen, then what we needed was a new multiplicity. So like I said, that's what that one part was telling us when I was trying to explain multiplicities. So once again, we have x is equal to 0, we have x is equal to -1, and then we have x is equal to 1. Here we had a multiplicity of 1, so I'm just going to write mult is 1. This one came from this factor, so it has a multiplicity of 6. And this one came from this factor, so this is a multiplicity of 2. So we're just going to graph those. So we have a 0 here, a 0 here, and a 0 here. So like I said, we know long run behavior should be kind of this shape. So when we hit -1, we hit that multiplicity of 6. So we should come up, touch, turn away. At 0, we have a multiplicity of 1. So that means when I turn back towards it, I go through. And then I need to turn back and hit this one. And just to make sure we did this right, multiplicity of 1, or sorry, the 0 at 1 had a multiplicity of 2. So roughly our graph is shaped like this. I'm just trying to smooth it out a little bit. Like I said, if you want to, you can graph it, but that's just a rough shape of it. Here we have a multiplicity of 4. Not multiplicity of 4, I'm sorry. We have a power of 4. Talk about multiplicities too much. So because that leading term, we know it should open up at the ends like this. So this is when we did factor earlier. So when we factored it, we got this. It factors into x plus 11, x minus 1. So I have 2 zeros. I have a 0 at -11 because of this one with a multiplicity of 1. And then here I have another one, oops, +3 with a multiplicity of 1. So we're going to kind of rescale this a little bit. So let's say this is like 2, 4, 6, 8. Let's go a little further than that. Let's make it 3, 9, 12. So I have one of my zeros is about here at 11, -11, and the other one is here at 3. So because we have, like I said, multiplicities, oh, we have an x squared. Never mind. We had more to do on this one. I didn't realize we had squares there. Let me go back and redo that. You see? Sometimes you just got to pay attention, like I did not. Okay, so we have that 4. So this turns into, we can think of this is looking like x squared squared plus 8x squared minus 11. So if we were to factor this, we would have a x squared minus 11 plus 11, sorry, and then an x squared minus 3. So what my zeros would actually end up being is that I have two choices. Here, we're saying that x squared equals negative 11. So we don't actually have any zeros there. The other one is x squared could equal 3 for that to be a 0. That means that x would have to be plus or minus negative 3. So in this case, we kind of ignore the factor because it's not actually providing us any zeros. This is the only one that provides us with zeros. So you could actually think of this as being like this. So it's just building those factors back in. So we know long run it looks like this. And then both of these have a multiplicity of 1, so I should only just cross through. All right, so for this one, we have this polynomial, m to the t. So when I graph that, I'm going to change all the t's to x's so Desmos can handle it. But 0.5 t to the fourth plus 3.45 t to the third minus 96.65 t to the second plus 347.7 to the t is used to estimate the milligrams of ibuprofen in the bloodstream t hours after 400 milligrams of the medication has been taken. So using graphing technology, we want to find the milligrams in the bloodstream at 0, 0.5, 1, 1.5. So like I said, this is hours after. So roughly every 30 minutes, we want to see how much would be left in the bloodstream. Here. So we need this. So this is your function graph. So it looks like this. So really the only part of this we need is this part right here, because we're only interested in what happens after you take medication. So we have to look at positive hours. Oh God, just wanted to rescale it. And what we're really interested in is in this part right here of the graph, because we were asked what was going on up to 6 hours after the medication is taken. So sometimes when we hit a 0, a lot of the stuff in the real world sense doesn't make any sense. So in this case, we're taking medication. So how much is in the bloodstream? So you take the medication, it has to dissolve in your stomach, your blood, then the cells start taking it into your blood. So the concentration would go up and it should go down. So this models it, but this only models it as long as we're looking at, well, technically t, but as long as we're looking between 0 and 6. So this is why we sometimes care about zeros, is because in this case, this function is only useful between two zeros. It's only useful as at this point at 0, 0 and at 6, 0. But then if you want all your concentrations, hit here. So we start at 0, 0.5, 1.5, oops, sorry, 1, 1.5. So as we see what's going up, going up, going up, we hit here at 1.5, looks kind of like a maximum maybe. Well, let's see what happens at 2 hours. Oh, sorry, 2, it looks like a maximum. Let's see what happens at 2.5 hours. I was looking at the wrong one there. And what we see is the values start going down. So that's all we were just looking at, just kind of analyzing this. But what we see is that when we have like I said, a polynomial can represent a situation, doesn't mean that the whole polynomial represents a situation. In this case, because we're talking about this medication in the bloodstream, what we see is it increases, it peaks at about 2 hours of your concentration and it slowly dies off. And technically we have a whole bunch of extra graph or extra function. There we go. Sorry, I was losing my arrow. But this part here is useless because you're not going to have a negative concentration. And if the medication wore off in your bloodstream, it's not going to suddenly shoot up. So sometimes when we have polynomials, we're just interested in what happens between two zeros because that's the only part of it that makes any real world sense.